In today's era of machine learning, an essential query to address is how to keep training fast and reliable, as language models and their context windows expand, especially when computation is spread across bandwidth-constrained heterogeneous systems. Large language models, or LLMs, are scaling rapidly, growing in terms of parameters, data, compute, and, more crucially, context length, expanding capabilities across an ever-increasing set of tasks, while raising the stakes for training time, efficiency, accuracy, and eventual deployment. While traditional distributed training paradigms realize this demand through centralized computing clusters assuming high bandwidth, low latency interconnects, the emerging decentralized approaches enable democratized machine learning that spans many volunteer collaborators, drawing on heterogeneous resources around the globe. A technical challenge in this landscape is limited communication bandwidth. Parallelism strategies such as data, model, and pipeline parallelism primarily enable scaling beyond a single GPU, but they rely on frequent synchronization and activation exchanges, leaving communication as the dominant bottleneck in decentralized settings. A significantly more challenging and largely unexplored frontier is context parallelism in decentralized environments. Here, limited bandwidth and non-trivial latency bottleneck the training. Existing bandwidth-efficient tactics like quantization and sparsification can help, but they perform subpar compared to unaltered global attention. Nonetheless, context-parallel training is becoming critical for pre-training frontier LLMs that rely on extremely long sequences, routinely beyond 100K tokens in models such as Llama, DeepSeek, and Qwen, substantially improving the ability to capture long-range dependencies. In context-parallel training, each node processes a local chunk and broadcasts attention activations to all others at every layer and step. Since attention needs global key-value access, centralized clusters cope with high-bandwidth interconnects. But on commodity links, this all-to-all is prohibitive. We introduce a method that drastically reduces this communication requirement while preserving model quality, allowing decentralized systems on internet-grade 300 megabits per second links to match centralized convergence. The method exploits the low-rank structure of attention activations by keeping key and value matrices within dynamic low-dimensional subspaces. Empirically, we compress communication by about 95%, support greater than 100K token contexts, and track the wall clock convergence of 100 gigabits per second centralized systems. In context-parallel training, the context dimension is sharded across devices. The input is split into chunks, and each device computes local query Q, key K, and value V from its shard. Now, since attention requires global access to all keys and values, every device must materialize the global K and V before applying attention with its local Q. Recently proposed ring attention mechanism improves utilization by pipelining this exchange in a ring topology, circulating key value blocks and accumulating partial outputs at each step. But the cost remains dominated by moving large K and V matrices, so communication bandwidth is still a bottleneck. Our approach is motivated by a simple empirical observation. Attention activations in pre-trained transformers live on low-dimensional manifolds. We measure the ranks of Q, K, and V activations across layers in public LLM checkpoints, and note a consistent pattern, where all three projections are extremely low rank. On Llama 70B, normalized stable ranks hover around 0.1% for Q and K and 0.5% for V across layers. This evidence underpins our low-rank factorization strategy, which we shall now look into. We exploit the low-rank structure of attention by communicating only the low-dimensional components of K and V. Each device computes its local K and V, projects them into a shared R-dimensional subspace U, and sends these compact coordinates instead of the full matrices. The receiver lifts them back with U transposed, recovering the activations to high fidelity whenever the signal lies in the span of U. This is equivalent to baking the projection into the attention weights factored through U times U transposed. So the overall transformer architecture is maintained at inference while communication during training is greatly reduced. A single fixed U, however, can be too rigid. If that subspace isn't expressive for a given layer or training stage, constraining optimization to it can push the model toward a suboptimal solution, motivating our adaptive subspace strategy. To overcome the limits of a fixed subspace, we jointly learn the subspace U and the mixing matrix B by factorizing the attention weights into B, followed by a projection onto U and back, and optimizing the original loss through this parameterization. The variables live on a product manifold. B is updated in standard Euclidean space, while U lies on the Stiefel manifold of D by R orthonormal matrices, and the remaining network parameters are optimized as usual. Using Riemannian gradient descent for U, together with ordinary gradient descent for B, yields a clean joint procedure that, under mild assumptions, enjoys linear and Q geometric convergence to a first-order stationary point. Optimizing U directly on the Stiefel manifold is costly because every Euclidean update needs a QR or SVD reorthogonalization. We address that by reparameterization of U as a fixed orthonormal basis U bar, acted upon a learnable rotation R of theta. With a sufficiently expressive mapping from theta to rotations, this covers the needed search space. With this reparameterization, each node caches the fixed U bar and transmits only a small rotation vector theta. Instead of exploring all rotations, we pick a few fixed skew-symmetric generators and let theta weight them, forming a k-dimensional rotation family via matrix exponentials. This remains expressive for training, yet far cheaper to communicate. We now extend the rotation trick into a dynamic mixture of subspaces. After a short warm-up, each node caches a fixed orthonormal frame U-bar as a prior, performing SVD on the attention weight matrices. Then, for every context chunk, a tiny feed-forward network psi looks at a summary of the local activations and predicts a chunk-specific parameter vector theta. Using a small bank of pre-shared skew-symmetric generators AL, the node builds a rotation by exponentiating a weighted combination of these generators, applies that rotation to adapt fixed U-bar to the current chunk, and compresses K and V by projecting into the resulting R-dimensional subspace. We transmit only the compressed activations together with their rotation parameters theta. Each node already caches the fixed U-bar, so upon receiving a message it uses this fixed U-bar with the corresponding rotation to reconstruct keys and values and then runs attention. The rotation dimension K controls the expressiveness bandwidth trade-off. The small feed-forward network has negligible cost. It scales with the feature dimension times K and is dominated by the usual attention compute, which grows quadratically with tokens. For small angles, the rotation is close to identity, as can be seen through a second-order Taylor approximation, creating a benign near-identity bias that keeps subspaces close to the warm-up phase fixed U-bar and further reduces compute. In low-bandwidth training, where context-parallel attention must cross 300 megabits per second links, our compressed decentralized CP tracks the centralized 100 gigabits per second baseline almost exactly in wall clock convergence, while the non-compressed decentralized run lags dramatically and converges far more slowly. Moving to throughput, the centralized 100 gigabits per second baseline sustains about 56,000 tokens per second. The non-compressed decentralized run at 300 megabits per second drops to about 2,700, and our compressed decentralized method reaches about 55,000, about 20 times faster than the non-compressed decentralized setup while essentially matching the centralized throughput. Thus, our work introduces the first compression method that enables context-parallel training in decentralized low-bandwidth settings. By projecting K and V into a shared low-rank subspace and steering it with lightweight per-chunk rotations, we match the wall clock convergence of centralized systems even over 300 megabits per second links and over 100,000 token contexts. The design stays compatible with standard transformer stacks since the rotation head and projectors can be removed after training, so deployment is unchanged.